Well, good morning. It's, I think 9:33 or something like that on Halloween, the 31st of October, 2016. This is supposed to be Calculus 2, but right now I'm the only one in the class, so hopefully the others will be coming in soon. Where we left off last time was on page 401. Well, let me say this too before I get started on today. As far as office hours go, this week is, as far as I know, going to be pretty close to normal until we get to Friday. Friday, I'm normally on the Birmingham campus, 7:45 to 11:45. Not this Friday, just like I was at last Friday. I've got my regular treatment this time. Last time was the first round, which was a reduced treatment to make sure there weren't any complications. There weren't. I did break out in a rash about midway through it, and they just cut off the drug, gave me more Benadryl, the rash disappeared, they started back again, no problem from then on. So it was not a problem. But that was 300 milligrams. This coming Friday is going to be 1,000 milligrams. Last time it took pretty close to 7 hours. This time, more than likely, it will too. So I'm starting at 7:30 in the morning. Actually got to be there for labs as soon after 6:30 as possible, and then start the infusion as soon after 7:30 as possible, and then hopefully be out of there before the end of the day. So anyway, Friday my office hours are shot. Now, just looking forward to next week though, on a Tuesday of next week, I have a doctor's appointment. My hematologist only sees patients on Tuesday mornings. So therefore, I've got the appointment next Tuesday. I don't remember exactly what time, but my guess it's going to mess up all three of my classes. My 8 o'clock class, my 9:30 class, and my 11 o'clock class. I might be back in time for the 11, but I kind of doubt it. But anyway, so that means as soon as I find out the time, then I'm going to have to rearrange those three classes to work in times to make up those three classes next week. Now, that means that sometime either this week or next week, some of my existing office hours will have to be spent making up those three classes or portions of those three classes. So anyway, there will be some other adjustments to office hours. I just don't know what they are right now. So anyway, that's as far as we know now. Now, last time we did finish the example 3, at least my mark indicates that, on bottom of page 400 and the top of page 401. And we were just past the midpoint in 401 where we have the situation. This was the last slide in that. So let me get my slides pen set up. Okay, here we go. And we were looking before, every one of them had been proper rational expressions. But what if that rational expression is not proper? In other words, P over Q is not proper. Now, what do we mean by that? What's the dead giveaway? If the degree of P is greater than the degree of Q, then this, or even equal to, it's not proper. So what we have to do then is use long division. And what we do then is divide P of Q, P of X, by Q of X, and you're going to get some, they call it G of X, okay, plus some new R of X over Q of X. Just like with long division, if a number P was greater than the number Q, then divide Q into P, however many times it goes, and then the fraction that remains, that's going to be, the remainder will be in the numerator, the denominator will stay in the denominator. Same thing with rational expressions. Okay? So, the next example shows an example of that. So I think I'll go on and erase this just so we'll have plenty of room to work. And here we have it. We're doing the integral of x, sorry, I've got to sneeze, x cubed plus 1 over x squared minus 4. Okay? And dx. Now, I sort of want to hear you say, hey, we can factor both the numerator and denominator, and that's perfectly true. The numerator is a sum of two perfect cubes, which can be factored. The denominator is the difference of two perfect squares. It can be factored. The trouble is neither one of the factors have anything in common. So it won't do us any good to factor. So then what we do instead is long division. So what we do is x squared. Now, here's what my suggestion is. You don't have to do it this way, but I find it easier. Anytime you're missing any terms, put a 0 in. X squared plus 0x minus 4. Divide that into x cubed plus 0x squared plus 0x plus 1. You do that sort of to be placeholders, just like you did when you're dividing decimal numbers. You know, you move decimals over and just make sure you have placeholders. Okay? How do you do this then? X squared into x cubed will go x times. Multiply x times x squared would be x cubed. X times 0x would be 0x squared. So you really didn't need that one, but you didn't know that for sure. And x times negative 4 would be minus 4x. Well, you did need that one, so go on and put them all in just to make sure. Okay? Now what you do, subtract, which for sign numbers is change signs and add. So make that a minus, make that a plus, and add. This will give you 4x plus 1. Okay? That remainder now has a degree less than your divisor, so therefore you have a proper fraction then. That would be plus 4x plus 1 over x squared minus 4. You don't have to put the 0 in anymore. Okay? So, what does that mean? This integral, since this fractional form here is that, all right, good deal. I was hoping I wouldn't have to talk with myself all day long. No problem. I know you're coming from the other campus. Yeah, I know. Makes it tougher.
It's not even from the other campus. It's it takes like 4 minutes for me to get here.
Oh, I see. Okay.
I'm like close to the UAB side.
Uh-huh. Okay. Yeah, I live in Forest Park, which is pretty close to UAB.
Really?
Yeah.
You take the freeway?
What's that?
You take the freeway?
Most of the time, yeah. Right. Sometimes when they're doing construction, I get off of it and come another way.
They do have construction. They have traffic every
Right.
evening.
Right. But when I leave in the morning, because I have an 8 o'clock class, usually it's a little better going west. It's worse coming in, but better going out. But by this time in the morning, it's probably bad both ways. Yeah. All right, what we're doing is example 4 at the bottom of page 401 in section 7.5.
If you don't mind, I have a question on
Okay, sure.
the quiz that you gave us, chapter 6.
Okay. Because I'll probably do something else. Let me go on and finish this one, then I'll answer that. Okay, just because otherwise then I'm not sure I could come back to the same point. Okay. So what we have here to set up this problem, then we'll answer your question. We had here a rational expression, but this is called improper because the degree of the numerator is greater than the degree of the denominator. Anytime it's greater than or even equal to the same, what you do is a long division. And that would be x squared, and that's what I did over here. So our numerator there now becomes, our argument here now becomes this, x plus 4x plus 1 over x squared minus 4. So this will now be the integral of x dx plus the integral of 4x plus 1 over x squared minus 4 dx. Okay? And of course, the first one's very easy, right? Yeah, that's all right. Take your time. Okay, what's the first integral? Integral of x dx. Antiderivative of x over 2. Right, there's the first part. Plus, now, this integral is like we were doing before. So I'm going to come over to the side here and just work on it some. Okay, this is going to be the integral of 4x plus 1 over, factor that denominator, x okay, it's x plus 2 times x minus 2, right? X squared plus minus 4. Yeah, difference of two perfect squares factors is that. Okay, and that would be a dx up here too. Okay, now, what we do here is then rewrite that as, I'll come down here and do it, 4x plus 1 over x plus 2 times x minus 2. We're hoping, this will be able to write as a over x plus 2 plus b over x minus 2. Now, it doesn't matter what you name that numerators. Let's see. They don't even show it. They just show you what the answer is. Okay? This is partial fractions. This is what we're doing. All right? What would be your next step? Yeah, and that would be the x squared plus x plus 2 times x minus 2. And what you do with it? You multiply it by both sides of the equation. X plus 2 times x minus 2. You multiply it by this term, x plus 2 times x minus 2, and multiply it by this term, x plus 2 times x minus 2. Okay? Well, here, obviously, your entire denominator goes out. And the first term on the right, the x plus 2 goes out, and the second term, the x minus 2 goes out. Okay? So what you have there is 4x plus 1 is equal to a times x minus 2. I have to wait till my thing catches up, sorry. Okay. Plus b times x plus 2. Yeah. I can't read my plus sign there. Okay, that's right. Okay. Now, what's your next step? Okay. Let x equal 2. And what does that give you on the left. X equal to 4x plus 1 is equal to.
Okay, so it's going to be B.
I'm sorry.
B4, right?
B. Okay. Here's Marcus. Happy Halloween. Okay. All right. I think he's a happy camper today, right? Okay. Overtime. That'd be one of the closest ones in history, huh? Yeah. All right. So what do you get here? Left-hand side when you let x equal to?
On the left-hand side, we get
9 is equal to? That goes to 0, right? And this is? Okay. Yeah, 4b. Okay, so what would b equal to? 9/4. Okay. Next. -2. And what would your left-hand side be then? Would it? -7 is equal to, this is example 4 at the bottom of page 401. Okay. Just a quick review here. What we have is a rational expression that's improper. The numerator is a greater degree than the denominator. Even if it was equal degree, that would be improper. So what we first did was divide, long division, and came up with x plus something that was proper, 4x plus 1 over x squared minus 4. Well, then when we do the x, that's easy, x squared over 2. Now we're doing the second part, and this we do by partial fractions, because you can't do partial fraction if the numerator is the same or a greater degree than the denominator. Now that we got it last, we can do that, and that's what we're doing here. Okay? So the left-hand side was -7. The right-hand side becomes? Okay. Yeah. When it's -2, that would be -4a, which would imply that a is equal to 7/4. Okay. Now, I need to do some erasing because I don't have enough room to work. So what I'm going to do is keep these and erase everything that was in between. Okay? How we got there. Am I erasing this too soon for you, Marcus? Okay. I'm trying to be careful, but my thing is not erasing well. Okay, those are my two values. Okay. Now, we'll rewrite the second integral as, I erased too much. I knew I was going to. This will be plus the integral of 9/4, because I erased too much, dx over, help me, that was the x plus 2, wasn't it? I think it was. Okay. And then it'll be plus 7/4 the integral of dx over x minus 2. Okay? I believe that's right. I think I got them in the right order. So this is x squared over 2 plus, what would that next one be? Antiderivative of 1 over x plus 2. Yes, the natural log of x plus 2. Goodness gracious, this drives me nuts. Plus 7/4 times natural log of absolute value x minus 2. And then finally, plus c. Yeah. All right. And I think that's the answer. I got my signs backward, didn't I? Okay. Because I knew when I erased that, I wasn't sure if I had them right or not. So this would be the minus there and the plus there. Okay. Is that right? Yes. Okay. Sorry about that. I knew when I erased it. Oh no, which one did I have over which? Okay. And there's your answer. So anytime that you do have an improper rational expression, do long division, get some polynomial in front, then you have a proper, your remainder will be a proper rational expression. And then you can use the techniques we've already talked about using there. Okay? But don't forget to integrate the polynomial first. This is what's x. It could have been longer than that. Okay? And then here we go. Any questions on that? Does that make sense? Okay. All right. Now, the next issue that we have, yes. Oh, yeah. Sorry. Thank you. Sorry. Okay. All right. To erase all the ink from the slide? Okay. Okay. You have a question on test 2, is that right? Okay. I have to find it first. It's in here somewhere. Here we go. I think I've got it. Here, I hope I remember where I put it. Okay, what you got? Number 5. Okay. Let me write it down because just right off the top I don't like one thing about how it looks. Find the volume of the solid generated by revolving the region enclosed by y is equal to x minus 2 squared and y is equal to minus x minus 2 squared plus 14. About the line y is equal to 5. Minus 5, sorry. Okay. Now what you got to do first, basically? Hint, hint. You almost have to graph it. I don't see any way around graphing this thing, okay? So, what I'm going to do is graph these in different colors. The first one, y is equal to x minus 2 in parentheses squared. How does that graph? Do you know? How would you go about graphing it to see? It's going to be a parabola. You're absolutely right. It's what? Okay. I don't know if you remember back probably in algebra or somewhere we talked about translation of functions. And this would be the same as y is equal to x squared. That would be the parabola centered at the origin, right?
Yeah.
But now you translated 2 to the right, and that would be right there. So that would be here, here, and there. There, and there. Whoops, not high enough, right about there. Okay, and then there be. Oh, I didn't draw this well. Let me start over my graph. Sorry about this. I didn't allow enough room. Well, I had the good idea, but it wasn't going properly. Okay. Let me try once more. Because now that I've taken just a glance of what it's going to be like, I should have seen this from the beginning. I'm going to put my axis way down here. Okay. We'll do 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7, 8, 9. Negative 1. Okay, I knew I had to get up to there. Okay. Now that first parabola is going to start here and then be there and there, there, and there. There and there. And 9, 10, 11, 12, 13. Somewhere up here. So here's that first parabola, something like that. Now the second one, I'm going to do in a different color. Not that I need to, but it may. You pick a color. What color you want it? Blue. Light or dark? Dark. Okay. So, now this one has a minus sign in front of it, but it's still starting at that. Well, now, and then it has a plus 14. So basically what the minus sign does is flip this over here, but then the plus 14 moves it up to there. So then you're going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I just barely got that in. So there's going to be the vertex of that one. Okay. I don't have it over too far maybe.
And the first one is -4.
What's that now?
X minus 2 squared, -4.
Oh, it's not minus 14? Yuck. Why did I rewrite this? Oh, wait. Isn't that x minus 2 squared plus 14?
That one is right, and here the first one is you have to have -4.
Okay, I don't. Where do you mean the -4?
On the first one. The first is.
Oh, I'm sorry. You're right. Goodness gracious, I didn't see that. Yeah, I wish you'd have caught me sooner. Okay. That's got, ooh. That has a -4. Oh, man. I need to redraw this again. Are y'all okay with that? Or, sorry, this is going to take way too long, but because I wasn't, like I said, I didn't see that. Let's Start all these over again. Whoops. I'm going to have to really do some scrunching here. Okay. Now, all right. One more time. Whoops, that's too high. This thing is so aggravating. There we go. Okay. Let's bring it down, but not as far as we did before. Okay. 1, 2, 3, 4. There's our minus 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's our plus 14. I could have centered it better, but can you live with that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We won't need all those, but I'll draw them in. Negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. All right, let's draw the first one again. Now it's 2 to the right and 4 down. There's your vertex. Okay? Right? And then 1 up from there and 1 over from there. Right? Then 1 here and 1 there. A 0 there and there. You see what I'm doing? It's a parabola. Its vertex is at 2, negative 4. And then from there you go up 1, up 3 more, which is a total of 4 from the bottom. And then up 9 from the bottom there. That's 4, 5, 6, 7, 8, 9. So that would be there and there. Whoops. Not all right in the right place there. Let me. Okay. All right. Then here would be, that would be 9, 10, 11, 12, 13, 14, 15, 16. That would be there. And that would be something like there. Okay. And then 17, 18, 19, 20, 21, 22, 23, 24, 25. Something like there and there. Okay. There's our first parabola. I didn't need all those, but I did them just to sort of fill in the blank. Okay. There's our first parabola. The second parabola is a lot like it, only it's flipped over but raised 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is going to be its vertex right here. 1, 2, 3, 4, 8, 9, 10, 11, 12, 13, 14. I didn't get it quite high enough. Right there. Okay. And then it'll come down 1 from there, there, and down 2, 3, 4, there, and there. No, I went over too far. Something like that. That's 4, 5, 6, 7, 8, 9. So they intersect there and there. I was going to do this in blue, wasn't I? And I forgot to. Okay. Its points are there, 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 and there. And then you could come on down. That would be 10, 11. Down here and down here, I think. So that parabola would be like this. Okay, something like that. Okay. This shape here, that curve enclosed in there, is going to be revolved around the region enclosed by y is equal to, oh my word, I didn't look ahead. Again, y is equal to -5. I was thinking it was x equal minus 5. It's y is equal to minus 5. It's down here somewhere. Now, technically, I ought to write this whole thing again, but you see the general shape?
Yeah.
Okay. I'm not going to be as careful with it, but I am going to do it again and try to get it. It won't be nearly that precise, but see if I can get this erased without destroying my problem. Okay. Sorry about this. On graph paper, I would have had all the room I needed in the world, but here I don't. Okay, so let's draw this again. Let me get my pen back to black. Okay. Here's my... Oh, man. Okay. I'm really scrunching it up this time. Okay. Something like that. And this was down to minus 4 here. Here's the line y is equal to negative 5. So this is revolved around that. So now we have the shape doing about like that. That's what it's going to look like. This is revolved around this axis. Right? So that's going to be like a donut. Well, even better than that, like a wedding ring. Okay? Where you have the curves up and below here going around, the axis is y is equal to negative 5 right through the center. Going around like this. Okay? So, we want the volume of the solid generated by revolving that. You tell me what you reckon we're going to need. Do we need to do dx's or dy's? You could do dy's, but my guess is dx's will work better. Let's just take a sample dx here. Let's take a sample here, right, and here. Okay, that slice there, here's your dx here, okay, this thickness here. What this is going to be is this thing is going to be revolved around the line y is equal to negative 5, and that's going to be the upper one, which is this one. That's going to be that minus this. So this thing minus a negative 5 is going to be the radius here. Okay, you're going to revolve that around here, minus this radius. That's going to be the thickness, the length of this, right? The top radius, and then you basically add 5 to that as well. So you add 5 to that and give you plus 19. Add 5 to this and you get plus 1. Okay? You see? And that length is going to be revolved around here. Okay? So that length times this width, that's going to give you a rectangular area, and then revolved around there. Well, that's going to be, the length of that is going to be it's basically just going to be the washer, is what they call it. That's what I was trying to think of the name. The washer is going to be the circle of this length, okay? So that radius is here. So pi r squared, no, I'm sorry. Yeah, pi r squared, that's the area of the outer circle, minus pi r squared, the area of the inner circle. There it is, there. And that's going to give you the area of this thing. And then you integrate from this point to that point. Now, I should have picked those points off before. One way to do it, I'm pretty sure that's from -1 to +3, I believe it is. I think that is, but you can check it this way. You set those equal each other. X minus 2 squared minus 4 is equal to minus x minus 2 squared plus 14. Add the x minus 2 squared to both sides. Okay, those go out, and subtract 14 from both sides. And that gives you 2x minus 2 squared minus 18 is equal to 0, right? And divide by 2, and that gives you 9, right? So that gives you x minus 2 squared minus 9 is equal to 0. Well, that's x minus 2 plus 3 times x minus 2 minus 3. Yeah, difference of two perfect squares. Okay. Equals 0. And that would be x plus 1 equals 0, or x minus 5 equals 0. So it would be x equal minus 1 to x equal 5. That's what I thought they were. X equal minus 1 here, plus 5 there. Plus 2 is in the middle. There's 3 over here and 3 over there. So that's right. So those are your limits of integration. And
then I'm going to add the -5 of both equations.
okay. Yeah. Then you're, let's just take, it may be easier to see over here. Here is your washer, or here is your disc here, okay? And that has a width of dx and a radius of the outer one minus 5, which is plus 5. And that pi times that squared, pi r squared, that's your radius here. That would be that one, and then you would subtract. So your first integral would be, and both of these are from what, -1 to 5 of pi, and then your radius here was I'm going to write it in a slightly different order. I'm going to write my 19 first, because 14 minus a minus 5 is 19, minus x minus 2 squared dx. I really don't need the first parenthesis, so I'm going to take that out. Yes, I do need that first parenthesis. Sorry about that, because I've got to square it. Squared. Pi r squared, that's going to be the area of that disk minus the area of pi times, and this again from -1 to 5 of, and that second one is going to be, and this one I'll write the other way. Yeah, this is a minus 5, I could either write it as a 1 plus that, or I could write, it doesn't matter, x minus 2 squared, what's that come up, plus 1 squared dx. Goodness gracious. Okay, and those are my two intervals. Okay, does that make sense? Yeah, it's the washer method, but it's, you know, it's an extension. If you go back, let's see, which chapter was that? That was chapter 6. If, yeah. What did you say? Yeah. It would be very much like on page 355, that figure, and the figure is on, it's not as good a figure, but it's like the, let me find it in the text. The summary was okay, but okay. It's like equation 2 on page 352, right about the middle of the page, where you just have to identify your R, that capital R outer, as the minus x minus 2 squared plus 19. And your inner is your x, the positive x minus 2 squared plus 1. You got to square each of those.
I have one more question, but I'll wait for end of the class if you have time.
Okay. All right. Either now or then. It doesn't matter. I'm sorry.
I don't want to stop whatever we're doing on chapter 7.
Right.
So if you don't mind, I can wait till the end.
Okay.
Ask from you, or do you have any questions?
Well, I mean, I don't mind answering them now because I only have basically 1 hour for lunch. So if we go at the end, then I don't have as much time for lunch. So I just, okay. But you got that one. Okay, sorry I had to draw it like 4 times or something like that to get it in there.
The
Question
question number 4.
number 4.
Yes.
Okay.
So
Let me clear this out. All right, to erase this? Okay.
I was stuck with the when I had to take the antiderivative from the.
Okay. Let me write down what 4 is. Find the total mass of a 3-meter rod whose linear density function in kilograms per meter squared is, and we have been calling this, did we call it rho or lambda? Whatever we called it. You remember which? It doesn't matter. Lambda? Okay, let's call it lambda. They call it y, but I'm trying to do like we did before, is 2 plus cosine x plus 1 over x squared. And this is good for 1 less than or equal to x is less than or equal to 4. So that makes a 3-meter rod with this as your linear density function. That's kilograms per cubic meter. So we're looking for total mass. So let's draw the rod here. Okay. Okay. That's the thing. 1, 2, 3, and 4. This is your x values. Okay? Now, we want the total mass of that. Right? Okay. Now, what we want is the
Do we have to take the entire derivative of the 2 plus cosine x?
say that again.
The entire derivative.
Okay. Yeah, let's take it a step at a time. This is the linear mass density, linear density function, mass density, kilograms per meter. Okay? So that means that any little segment here, we're going to do, say, a dx here. Okay? This will be our dx. Okay? Now, what is the mass of that density of that there? Okay? And this is kilograms. This is in kilograms per meter squared. No. Per meter, yeah. It's not an area, it's a linear. Okay. So that means to get the density of that little piece, we're going to have to do its length, its mass, its length times its length is dx. So yeah, exactly what you do here, you integrate from 1 to 4, this linear mass density, 2 plus cosine x plus 1 over x squared dx. Okay? Because this gives you the mass per unit length, that is your length, and you integrate that from 1 to 4.
I was talking, how can you take the antiderivative?
Okay. Well, you know how to take the antiderivative of 2, right? 2 dx would be 2x. This would be, it would be sine, wouldn't it? Positive sign, because the derivative of sine is cosine, so the antiderivative of cosine is sine. And this would be, I would say write that as x to the minus 2.
Okay, and then x to the, then x, right? Antiderivative of x. X to the minus 2 plus 1. Or minus 1.
Yes, exactly.
X to the minus 1. Okay, I got it. I came up to that point, and I was stuck with the antiderivative. I'm afraid what I'm doing.
Yeah, that's it. Yeah.
Okay, I got it.
Okay.
I feel like 6, 7, 8. At the 6 is like. Do I have to draw?
I'm guessing yes, but let me see. Let me read the problem more carefully. It's been a while since I made up this test. So let me look. 6. Find the volume of the solid generated by revolving the region enclosed by y is equal to cosine x and y is equal to minus cosine x. Yeah, I mean, and that's pretty, let's, okay.
I'm just confused that they give about the line y equal to 2 pi.
Okay.
It's like pi.
Okay. Let's first do this. You're going from minus pi halves, so let's call it okay, this is minus pi halves. Pi halves pi. Okay. And then I probably haven't left enough room. Okay. Yeah, I know I didn't leave enough room. Let me go. Why can't I get these right the first time? Okay. Try it once more. Okay. About the line y is equal to 2 pi. Okay. What in the world is it doing here? Okay. Okay. I don't know where my pen is. There we go. Okay. Try this again. I'm going to put my x-axis down here and have that be -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And this will be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 6, 7. Okay, I don't need that many. Okay. So let's do the cosine from minus pi halves to pi halves. If that's 1, minus pi halves is just a little over 1.5, right? Because pi is 3.14 and pi halves would be 1.57 or something like that. So 1.57 to 1.57 here. Okay? So cosine goes like this to there, and minus cosine goes like that to there, right? So that's your shape. That's the region. About the line y is equal to 2 pi. Well, there's 2 pi would be 6.28, right? So 1, 2, 3, 4, 5, 6. So right here would be your line y is equal to 2 pi. Something about there, right? So rotate this around there, and I probably didn't leave enough room, but you'd have another shape like this and like that, and rotate that around, just sort of like we did before. Almost exactly. Again, you get a ring, right? A wedding ring. Okay? All right? Okay? Again, I would do dx's, you know, and yeah, our outer would be your minus cosine x, because that would be farther from the line 2 pi, so that would be minus cosine x. Well, yeah, minus cosine x. Actually, you do a 2 pi minus a minus, which is plus cosine x, and that's the outer r, and the inner r would be 2 pi minus cosine x, because that would be the distance here. So those would be the radii that you do. Okay? Number 7. Now that one, they tell you shell method, so I'm assuming that's going to be the easier way to do it. But let's see. To calculate the volume of the solid obtained by rotating the region, your xy pair is going to be x going from 4 to 6, and y going from the square root of 8x to x squared. Okay? About the line x equal 2. Okay. So this time I'm going to put my vertical axis maybe here. Horizontal axis I'll just draw in here. I hope I get it about right. I need to be further over. Oops. Let's see. graph paper, you could take all the room you needed. I don't have it here. Okay. Probably did a little too much there. Let me move it a little bit further that way. About like that. Okay. 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4. Okay. I don't have my x-axis in the right place, but I'm going to try to get it okay. 1, 2, 3, 4, 5, 6, 7. I don't need any below there. Okay. So we're going 1, 2, 3, 4, from 4 to 6. Okay. And the square root of 8x. Okay. Well, 8 times 4, okay, the square root of 8x. And you're only going from 4 to 6 on x. So when x is equal to 4, this will be the square root of 32. I'm sorry, okay. Here is the line you're rotating around. Yes, sir. Did you finish? You finished for good? Okay, good deal. Thanks. Okay. All right. So we need to do the square root of 32 is going to be something less than 6, right? 1, 2, 3, 4, 5, 6. So we'll say that's going to be something about like that. And when x is equal to 6, that would be the square root of 48. That's something less than 7. Okay? So this is that portion of your square root function. Okay? Do you agree? Okay. That's the upper one. The lower one is x squared. Well, this is 0, 1, 1, 2, 4, 3. I haven't drawn this well at all. Let me start over again. I have to draw these so many thinking times. Okay. Okay. I don't know why my pen's not showing up. Okay. Here's going to be my x-axis way down there. My y-axis will be about like that. Okay? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Is that going to get me enough? No. I need to go to 36. So 10, 15, 20, 25, 30, 35, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 3, 6, 9, 12, 15, yeah, 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36. I think that'll get me where I need to go. All right. I'm going to do a different x scale. 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4. Okay. So we're going from 1, 2, 3, 4 to 1, 2, 3, 4, 5 to here. Okay. This is the only region on x. Okay. Your y's are going from the square root of this is something less than 6, so something about like there, to something less than 7. So this is that portion of our square root function. Okay? Your y values are going, the upper curve is going from 16 to 36. Here's 16 here to 36 there. Okay, and this is that portion of a parabola. So this is what you're doing. Oh, I'm sorry, I drew that poorly. It's going, this is straight lines here and straight lines here. Okay, you're revolving that around x equal 2. Right? Yeah. So that means this flips over to here, and it goes from here to there, and this flips over from from here. Goes from here to here, and this goes from here to there. Okay, I don't have this, no. This is not doing well. Okay, something like that. Okay, this is the region, and you're revolving it around here, around that line that way. Okay, now obviously here, I hope you see you've got to do a shell method, which is going to be a dx, right? Okay, so you're doing a shell all the way around here. Your length of this thing is going to be your x squared minus the square root of 8x. That's going to be the length of that from here to there. Okay? The width is going to be dx. And then you're doing this 2 pi r, 2 pi. Now what's the radius? The radius is x minus 2. Because it's x going from 4 to 6 minus 2, that's going to be the radius of this. X minus 2, that's going to be your radius. So 2 pi r times the length times the width. And you integrate that, and of course the 2 pi can be on the outside from, the x's are easy. X is going from 4 to 6. You don't even care about what the y values are there. They're whatever they are. That's all taken care of in the wash. Now, it's not a really pretty integral to do, but it's certainly doable. You have to expand this, multiply, FOIL this, do it. It's going to be a little messy, but not bad. Not terribly bad. Okay? Does that answer what you need? Is that all of them? 8. Okay. Let's see how many times it takes me to draw this one. Consider the region enclosed. See, really the hard part of these problems is drawing the graph. And like I said in the book drew them for you. You're really lucky. Here you have to figure out yourself. Consider a region enclosed by the graphs of that. Let me read the whole problem this time. Use the shell method to compute the volume of the solid obtained by revolving that region around the line x equal -6. Okay. Here's my guess. I hope I get it right the first time. There's going to be that. And this is going to be something about like this. I hope I've got my axes right now. Okay? Okay. I sure hope I've got enough, okay? If I don't, we'll fudge it, or we'll try to. Okay. Okay, something like that. Let's draw the first graph. Y is equal to x minus 2 squared. We did almost this one before. It's a parabola displaced like this. I'm not going to fill in the dots for you as nicely as I did before, but it's going to be basically a parabola like that, right? There and there, there and there. Okay. Something like that. Okay. I hope that's close to it. Okay. Now, the second one is parabola minus x minus 1 squared plus 13. Okay, so that's going to be centered at 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I didn't quite get it big enough. But you get the idea. It's going to be somewhere up here. It's going to be at 13 up there. Okay? And it's going to go there, and basically something like my parabola is pretty lousy. Okay, so now you have to figure out what your intersection points are, and that's setting those two equal to each other. X minus 2 squared is equal to a minus x minus 1 squared plus 13. Now this we're not going to be able to do as nicely as we did before because that was the same thing in parentheses squared. This one you got to multiply these out. That'd be x squared minus 4x plus 4, right, is equal to minus, sorry, x squared minus 2x plus 1 plus 13. Right? And this will be, when you subtract that, it will be a 2x squared here. And this is a minus 4x, and this will be a plus 2x, but you're subtracting, so that's going to be a minus 6x. That's a plus 4. It's going to be a minus 1. That's going to be a plus 12, but subtract minus 8, I think. I'm doing this quickly in my head. And set that equal to 0. That would be x squared minus 3x minus 4 equals 0. Be x minus 4 times x plus 1, right? I believe that's right. So this is going to be x equal 4 to x equal minus 1. So here, hey, look at that. X equal minus 1. And this one is going to be x equal pretty close to 4 here. Okay. Okay, if I had drawn that right, that would have come right through there. So that's going to be your interval of your dx's. Okay, this is going to be revolved around the line x equal negative 6. 1, 2, 3, 4, 5, 6. Okay, so this shape over here, and, you know, that, oops, I went too far down. Well, something like that. That shape is then, this is what the revolution is. So the shell method will again be a dx, and your length is going to be from this curve here to that curve there. So this one minus that one, that's going to be the length. The width is going to be dx, and the 2 pi times the radius. of the radius here, your x here. Remember, your x is going from -1 to 4. And this will be x minus a minus 6. Yeah, so x plus 6. That's your radius. And then your height is going to be the difference between this and that. Does that make sense? Yeah, the length is this one here, which is this upper one here, minus the lower one here, which is this one. Okay, just that length, dx, and then your 2 pi r is 2 pi x minus 6 times the difference. So it would be this thing minus that thing, which is a little bit of a pain, but you have to multiply them out and do pretty much what we just did. Does that answer the question? Okay. All right, any others? Okay. All right. How are we doing on time? It's what? I can't hear. 10:50. Okay, so we've got another 20 minutes, right? Okay. Because we go to 11:10, right? Okay. All right. So, where was I? Okay. Oops. What's that? Right. No problem. Okay. All right. We've done example 4, and we got an answer to it. Okay. Where we were going to go next. Sorry, excuse me. Let me erase all the ink. Okay. Quadratic factors. Sometimes you have a quadratic factor that you can't reduce. Okay? ax squared plus bx plus c, that's irreducible. And you know what those are, basically. If it cannot be written as a product of two linear factors without using complex numbers. Okay? Now, a power of an irreducible quadratic factor, m, what if you had that raised to the mth power? Okay? It contributes a sum of the following type. Now remember, irreducible is anything that you can't reduce it without having complex numbers. Remember, you can use, make sure I'm saying this right. I was going to say you can use irrational numbers. Let me stop just a minute and think about that. Yes, you can use irrational numbers, you just can't use complex numbers. Okay? But most of the time we're going to avoid even irrational numbers. Okay? But that's irreducible if it cannot be written as a product of two linear factors without using complex numbers. Okay? Now, what if we then raise it to a power? It contributes a sum in the following type to a partial fraction decomposition. Okay? So let's say you have a a1x plus b1. Now, see, this is a little different. That would be ax squared plus bx plus c plus, and then you'd have a c1x plus, oh wait, no, they call them a2s and a3s, though. They change around how they name these, but it doesn't matter. They're just, it would be a2x plus b2 over ax squared plus bx plus c squared plus, and then you just keep on going, a3x plus b3 over ax squared plus bx plus c cubed all the way up dot, 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 until you get to A, is it N, M, I forgot what they called it, mx plus bm over ax squared plus bx plus c to the nth power. Okay. Just like we did when you had a multiple of a linear factor, remember you just kept doing a1 over x minus a, x minus c, plus a2 over x minus c squared plus a3, yeah. You just kept doing it that way. Well, now you, since this is an irreducible quadratic, your numerator is going to be a linear, not a constant. If you had a linear down here, the numerator is a constant, okay? Because they're always one less degree. And then if you had m of those, multiplicity of m, then you have one for the first power, one for the second, one for the third, one for the fourth, up until you get to the nth power. But your numerators are all the linear forms. Okay, so that's the only difference here. Okay, and here's an example. So let me clear this out of the way. Sorry, my head's all clogging up again. What if you had this? 4 minus 12x over x plus 1 times x squared plus x plus 4 squared. Okay. Now, obviously this has a linear factor, right? Quadratic, partial fraction, you have a linear. This quadratic, without the square on it, can you factor that? No, you can't. Here's the giveaway. Remember in the quadratic formula, right? That thing under the radical we call the discriminant. That tells you what kind of an answer you're going to get. And it's b squared minus 4ac. Remember? Well, b squared here in this case is what? Minus 4 times 1 times 4, that's minus 16. 1 minus 16 is negative 15. The square root of that is complex. You can't do it. So this is irreducible. That's how you tell if it's irreducible. Do your b squared minus 4ac. So since this is irreducible, you can't factor it, okay, then you do it this way. Well, over the linear term, what would be your partial fraction? A over x plus 1 plus, okay, and since this is a quadratic that's irreducible, you have a linear here, call it b1 x plus c1 over x squared plus x plus 4. That gives you the first power. Then you need another one, b2x plus c2 over x squared plus x plus 4 squared. Exactly. Okay? Now, from here, you then go through the same thing you did before. Multiply both sides of the equation by the least common denominator, which is that factored form. And that would get you a number on the left, 4 minus x, 12x on the left. On the right, you would get that times your x plus 1s will go out, and you get a times a fourth power of this, right? You get this thing squared, so you have x to the fourth and x to the cubes, and you'd have that thing there. And then you'd have to square that. Then on that one, you would have the b1 x plus c times x plus 1 times one of those again, okay? Because one of them divides up. And on the last one, then you'd finally have one that would have a b2x plus c2 times x minus 1. So this whole thing would go out. Well, then you could substitute in x equals -1, you take out some of those, and you get one thing. But the rest of them, it's a lot more work. Okay? There aren't any easy answers from there on. Okay? We'll see that a little bit later. This one is a wacko problem that they gave you. They didn't carry it any further, so we're not going to do either. Okay? But here, they have a hint. You may need to use trigonometric substitution to integrate these terms. For instance, this one. Okay? I don't know why. I know why, but it shouldn't have. Okay. When you get down to a stage that looks something like this, when you have these irreducible quadratics that you can't do anything else with, get it into a form like this, and this will give you an arctangent. Okay? Remember what that is? 1 over square root of a. If this was an a squared, that would be 1 over a. But with being an a here, it's 1 over the square root of a, and then this would be the inverse tangent of x over the square root of a. If that would have been an a squared, that would have just been an a down there, plus c. Okay? Now, you might say that last one didn't look like it was going to turn out that way. You can get it to by completing the square. Remember how we did that before? Okay. I think we'll see some of these in our examples, so I won't belabor it. Do we have time to do example 5? Oh, we got 10 minutes. Let's try to do at least example 5A. Okay? And B is actually even easier, but let's try this. Okay? All right. Here's our first integral. 18 over x plus 3. That looks good for partial fractions. But this one, x squared plus 9, that doesn't look quite as good, dx. Okay? What are you going to have to, what will be your approach to that? Let's pull this out. 18 over x plus 3 times x squared plus 9. What would be your partial fraction? Say again? A, is that what you said? A over x plus 3 plus bx plus c over x squared plus 9. Very good. Now what? Multiply both sides of the equation by that denominator. So basically that's going to wipe this one out. That will wipe out the x plus 3, but this will be an x squared plus 9 here, right? Wipe out the x plus squared plus 9 there, and this will be times x plus 3. Follow it so far? Okay. Now, first thing to do, second, what? Excellent. Let x equal -3. So here you still have 18, right? Over here you get what? A times 18. Perfect. Okay? And over here you get, that goes to 0, right? Okay. So that gives you A is equal to, say again? 1. Perfect. Okay. That's where your luck runs out. Okay. From this point, you have to do the B and C calculations just based on what you've got. So let's go back and show it before. You have 18 is equal to x squared plus 9, because A is equal to 1, plus, and now you have to multiply those two together. And that would be bx squared, I don't really, oh. I don't need the parentheses anymore, so I'm going to take it out. Okay. Okay, that's bx squared plus 3bx, right, plus cx plus 3c. Do you buy that? Okay. Because you had a is equal to 1 already. All right. Now, let's look at the x squared terms. On the left, what are your x squared terms? There aren't any. So at 0 is equal to 1 plus b, right? Your two x squared terms over here are 1 plus b, right? And you don't have any on that side, so that. So this would indicate that b is equal to -1, right? Now let's do the c term. We got a, we got b, all we need is c. Now, we could go through the x terms, but why? Let's not. Let's just look at the constant terms. The constant terms is 18 is equal to 9, and it could have been the other way. We'll go back and do that too, plus 3c, right? Those are your constant terms, right? Okay. So what does that give you? That gives you 9 is equal to 3c, which implies that c is equal to 3. Well, let's say, no, I really wanted to use the x terms. Let's see what we had there. Okay, we had for the x terms 0 on the left because there weren't any x terms. And on the right we had is equal to 3b plus c. But b was -1, wasn't it? Whoops. I hit the wrong button. Wait. Okay, goodness gracious, I lost my whole thing. B was -1, so this was a -3, right? I wish I'd have done it this way. This is even easier. What does that tell you? C is equal to 3. So either way, you got C equal 3. I just picked the other one because I thought it'd be a little easier. It wasn't. This one was actually easier. But they're both easy. Okay. So we've got what the three things are. A is equal to 1, B is equal to -1, and C is equal to 3. So we go back and rewrite our integral. So I'm going to erase everything I don't need here. I hope I don't erase too much. Okay. I don't think I need this anymore, nor that anymore. I hope I don't need it. I sure don't want to reproduce it. Okay. I don't need this anymore, but I do need that. I don't need this anymore. I only need 1, C is equal to 3, so I think I'll leave the 1 down there. Those are my three constants. Oh, I did need something else. Why do I always forget that? Okay. So what was this going to be? This is going to be the integral of dx over x plus 3. That was my A, remember? Plus, I'm sorry I forgot that, plus the integral of, now my B was minus x plus 3 over x squared plus 9 dx. Wasn't that right? That was bx plus c, which would be minus x plus 3 over x plus 9 squared. That was it, wasn't it? Okay. Now, what do we do? First one I think we can do, right? What's that going to be? That integral there. First integral. Yeah, natural log of x plus 3. Got it. Absolute value, really, technically. Plus, now let's see, what are we going to do with this one? Let me suggest to you what I would do, I think, first. Let's split that into two integrals. Minus the integral of x over x squared plus 9 dx plus 3 times the integral of dx over x squared plus 9. Do you see what I've done? I did the minus x over x squared plus 9 first, and then plus 3 over x plus. Right? Is that okay? Now, this one, don't forget the log, natural log of x plus 3 minus. Now, what can you do on that one? Second? I can't hear you. I would say a substitution. What would you let? Let u equal x squared plus 9. du is equal to 2x dx. Well, just do a 1/2 because 1/2 the integral of du over u, right? Okay. We'll come back to that in a minute. Plus, now this one, look at what we got right down here. Got it on the screen for you. 3 over, and it's dx over x squared plus 9. That would be 1 over 3 times the inverse tangent of x over 3, and then we'll have our plus c. The plus c we're going to do at the end. So that's a log x plus 3 minus 1/2, and what's the antiderivative of du over u? Log u, right? ln u, right? Okay. But your u is x squared plus 9. So it's minus 1/2 log of, now this one I don't need absolute values on because x squared plus 9 is always positive, right? Never 0, never negative. So you can put parentheses around that one. Plus, and here you have a 3 on the outside, a 1/3 on the inside. Those go out. Inverse tangent of x over 3 plus c. That should be our answer to the A. Okay, let's see. I got ln, absolute value x plus 3, minus 1/2, natural log of x squared plus 9, no absolute value bars, plus inverse tangent x over 3 plus c. Now, I take it we're out of time. Okay, the B part's even easier. Okay, I know you found that super easy, so we'll start with the B part next time. Okay, which means top of this page right here. We'll start there. Let me give you a few homework exercises here. We almost finished 7.5. You could do 1 and or 3, up to you. Either 5 or 7 or both. Any of the odds 9 through 9 through 35. Okay? You might be able to do 37. I'll let you. No, you could do 37. That's not too bad. You could do 39. 41, I think. 43 may give you a little bit of a problem. So go through 41. You can go further if you want to. Okay? and we'll pick up in the B part next time. Good deal. Any questions? All right. All right. Sorry I took so long on the test questions. If I could only draw, I would have had it much quicker. Okay. All right.